things to get out of the way. First and foremost, we finally got parts delivered. I ordered stuff from Mouser a while ago, and it took them forever to deliver it. And so now I have a little control board, I have buttons, and then I have these slide switches as well. Here, I'll pull one off to show you closer. It looks like this. So these are just the little slide switches off of sound mixing devices. You can buy them pretty cheap. These were like $1.50 each. And then the switches are just simple, or the buttons are just little push button switches. Pretty good stuff. So right tonight, oh geez, it's been a while streaming, so I got to get back into it. Tonight, we're going to try and wire up the circuit and get kind of a test circuit working, and that way we can start proving that these components work as expected, and then we can go from there. And once we prove that that works, we can write enough software to show that it will interface correctly and that this MIDI controller will work as expected, and then we can go through and design the circuit board and then the whole assembly from there. So it's cool to finally be at a point to where we can have actually something functioning on the desk and not just have it all be on the computer in, a model or something. So let's get started with that. So tonight, let's see, I'm going to go here and let's see, I need to change our current goal here because we have in fact finished updating the schematic. Let's see, wire up the test circuit, I guess. All right. And then I'm going to make that a little bigger because it's really tiny. There we go. All right. So for tonight, you can see I have our schematic up here already, but for tonight, I hope to just get this done and get a little bit of code started to prove that it works, that the circuit is at least sort of functioning as we expect it to. We'll see how it goes. Like I said, it's been a little while since I've streamed, and I know it's been kind of hit or miss the past couple weeks. I'm trying to get back into a regular schedule. Just had a lot of stuff come up. All right. So let's get started. I'm going to turn the music back on so that we have something to listen to. And then if you have any recommendations regarding the volume or tips to help me out as I'm doing this, please let me know. But otherwise, I'll move that out of the way so y'all can see what I'm doing. And I'm just going to go back to this big screen here. So first and foremost, these control boards, as you can see, just have a bunch of little connector pins. I know it's kind of hard to see because it's so tiny. But there's not actually like pins sticking off this thing, and that's what I need to connect it to a circuit board or a breadboard. So I have a couple of headers in this breadboard here, and I'm just going to solder it down on, make it a little more permanent. So let's let this heat up. And, talk about whatever, ask me whatever. Let me know how your week's going. Hopefully everybody's having a good Thursday. Let's see here. I want this to be a little hotter. I know this is a little weird. I got the mic way over here. I'll try and move it over some so you can hear me better. All right. Let's get started. Hopefully my upstairs neighbors aren't too loud too. Usually when I start streaming is when they like to stampede across all over the place. So go. This is going to take a bit. There's a lot of pins here to do this too. How many? 2, 1 through 11, 12, 13, 14, 28 pins. I got to solder down 28 pins. All while without burning myself, which is a daunting task. And try not to breathe in too much of the smoke. Did I get that one? Yeah, I got that one. All right. Hopefully I can pry this whole thing out of here once I'm done. I think what I'm going to do initially is just connect one of these slide switches and one of the buttons just to test that it works, and then go from there. And then I'm going to try and, I have a schematic pulled up as well, and I'm going to try and connect everything based on how the schematic is. So that should at least verify that those pins can be used the way we expect them to be used. Can you all hear the music? I was having some trouble with the software before. So if you wouldn't mind, let me know if you can hear it or not. All right, there we go. Got the breadboard done. Now, I got some wires here. Basically, we're just going to solder wires directly to the pins on these different components because there's not really a good way to do it. They're kind of designed to drop into circuit boards. So we got to do that to check them. I'm not sure how the best way is to do to this one yet. We'll figure that out. Okay, I'll start with the switch though. Switch needs a ground and a power side. That shouldn't be too hard to do, especially with these jumper wires. All right, I grab this thing. To hold it up. Gotta figure out the best way to do this. So everything's out of the way. All right, come on. There we go. Okay. Now I need a little bit more solder. Yeah, I was a little worried that tonight I wasn't going to have like much to do or be kind of out of it because I'm just not used to it. I've had so many nights where I didn't stream that I've kind of slowed down a little bit, but I'm glad to be back here doing this, working on these cool projects. That looks good. I gotta be careful too, because all this plastic and rubber parts, the soldering iron here will just melt them if I touch it wrong. So I gotta try and do everything without hitting the wrong thing. Okay. It's gonna be even harder to do the other one. How's everybody's night going? Everyone having a good day? All right, there we go. We should probably run this through a resistor to the ground, actually, now that I'm thinking of it. Now we'll figure it out. Alright, now I gotta figure out how to do this one, which I'm not really sure about. We'll see, though. Let's see. If I hold this... Oh, what's the best way to do this, even? There's not really a good way, that's for sure. Maybe just hold it by the switch there and just do this manually. The way this is labeled is really weird too. I'm actually going to go look at... Here, I'll show you. I'm going to go look at this real quick. Let's pull up the design. Just so I can make sure I connect everything to the right pins. If it loads. My computer also decided now would be a good time to do a bunch of stuff in the background. Any second now. There it is. Alright, need the 2D view of this. Okay. That bottom pin is, did I label this right? 3, ground. Yes, okay, I think it is. Does look like I at least labeled them right according to the schematic. 2, 3, okay. I think that makes sense. Sorry, I'm just trying to line up the pins with the ones I see here. Okay. Let's try one here and see how well this goes. Put some solder on it. And then put some on here. And then connect the wire to it. I think that worked. I'm trying to do it in such a way that I can scrape the solder off later too to actually put it on the PCB. Okay. All that smoke is just, I don't know if you can even see the smoke on the stream, but there's so much from the flux burning off. like that could be connected a little more. Yeah, we'll roll with it for now. All right, one more. All right, let's see. I think that holds. Okay, good. I think that works. I really need a resistor. I thought I bought some, but I don't know where they ended up. I could have sworn a bunch came in the box I got. I hope I didn't throw them away. They were pretty cheap, so I'm not too worried about it, but still. What we got in here? What is this? 220. That'll work. Right? Orange, orange, brown. It's 220. No, it's a 330. That's okay. That's still acceptable. I'm going to put this between the ground of the button and the actual ground. All right. So I can turn this off. I think we're done soldering, hopefully. And then take this apart. And go back here. All right. Let's see. I guess I gotta go look at my schematic again. Here we go. And let's go here. All right, so for the button, let's just do switch 1. Ground. We need to go to ground, which would be pin 1 on this. They're actually marked here too, which is useful. Okay, but I think I said, yeah, I was going to do it through a resistor. Let me get another wire here so I can run power to the bus. All right, and then I need a 3-volt. Okay. And then this input goes where? Switch 1 goes to pin 2. No, goes to the pin label 2, but it's actually pin 4. Okay, there's our button. And then our slide switch. Well, slide potentiometer. I'm going to mess up so much terminology tonight. It's going to be great. All right, so we got power. Hopefully these don't snap off while I'm connecting it. I wish I could drop this on the breadboard a little better, but that's just not really possible. All right, and then this plugs into, let's do channel 19, so A0, which is pin 21, 14. Yes, slide thingy. We got to get all technical. Put the nerd hat on. Linear potentiometer. Although not always. Sometimes they're called linear potentiometers. Sometimes linear potentiometers are actually like these little piston things, and instead they call these slide potentiometers. And then some websites consider them the same, call them a linear or a slide potentiometer. It's confusing. All right, so labeled 14, but actually pin 22. Okay, that should be pretty basic. So one button, one slider. I guess now we just gotta write some software and just see if we can tell when these things are happening. And then, so something else that was interesting, I realized that I had overlooked something initially, and I was looking up. So this MIDI controller kind of thing has more or less a standardized protocol, and they're not logarithmic. It depends. You can buy them, depending on how you want it. And in this case, this one is linear. So, something interesting. But I think and what I'm saying, when I say linear though, as in linear potentiometer, what I mean is the motion is linear. It might actually be a logarithmic resistance, but when they say linear, what they refer to is a straight line motion potentiometer to control the resistance. Okay. What was I saying? Oh, the protocol is everything I was reading. It was like the standardized protocol. But it turns out that's actually on the actual MIDI interface cables, which is that weird 5-pin round connector. Evidently, that's a serial cable, and it's a high side, low side serial cable, and that's the communication protocols that I'm reading were specified for that specifically. And I need to know what the USB protocol is, and I think I found the document on it that more or less says it, but I'm not totally sure how all that works yet. So. The good news is micros are pretty flexible, and you can implement just about any type of stack protocol that you need to. And we know for a fact that this can be done over USB because other people have done it. So, it's just a matter of finding the right thing. But for now, we're just going to read the analog values and read the button input and print it to the serial port just to make sure all that works. And then we'll probably expand on that and put in some like debounce and some smoothing out of the potentiometer motion and everything, and maybe even get some interrupts working so that it's callbacks rather than pulling, constantly. All right. So let me go ahead and we've wired up our circuit here. Quote unquote, it works. And let me change our current goal. So now we're going to write the low-level software. Right, the right word for this is hardware abstraction layer. It is good practice when you're programming with micros and such. I know that's off the screen. Hang on. To write something called a hardware abstraction layer, which effectively is a layer between all of your actual application code and all of your interfaces. And what that allows you to do is easily move the software from one thing to another. So for example, this board was discontinued or out of stock and I had to pick something else. As long as I have an abstraction layer, then when I move it from one to the other, all I have to do is change what's on that abstraction layer. And then I know that everything above that, all that C code will still work just fine because it doesn't actually interact with any of the peripherals directly. A lot of words. Okay. I bet when this is done, I just had a great dumb idea. Whenever I get this working and figure out that protocol, I should probably set it up, write my own script to interface with it on the computer, and then have that interface with the Falcon as well, and then I can control the colors of the Falcon using the sliders. That'd be kind of cool. Okay. So let's see here then. I think I've already set this up. Yep, with TNC4, USB type serial, standard speed, 600 megahertz. For anyone that's not seen this, I know it's really hard to see because it's pretty small, but I can select the clock speed on this. I can select as low as 24 megahertz. Its standard is 600, or I can select 1 gigahertz. But anything above like 900, it recommends that I put some sort of heat sink on it. Otherwise, it'll get very warm, and I might kill the chip. So I'm not going to select any of those. I think the standard 600 is fine. But I just thought that was crazy. Like, it's amazing now for a few dollars what kind of processor you can get. You can run at gigahertz. And this particular processor too even has its own little integrated 2-dimensional GPU for drawing 2-dimensional shapes and running interfaces that way. So it's not gonna be much longer before micros are gonna have everything in them. I should try and get like Windows XP to run on it or something. That would be a great dumb project. It probably wouldn't work, but a fun port. Okay. Let's see here. I gotta remember how to do Arduino. Real dot. Does it begin? Yeah. And 15200. And then let's do delay Slackware. Yeah. Oh, I already forgot a semicolon. That's just how things go. All right, so first things first, we should probably make sure that we can connect and run this thing. And so serial dot print hello world. All right, let's verify this. And then hopefully this doesn't like crash anything. I was having issues earlier where I was having too many USB ports plugged into the same bus, and like random things like my microphone and camera were just dying. We are setting up a device. All right. Looks like this compiled. No issues. Device is ready. Okay. And then, so let's upload it. Tools, ports menu. Oh. I got to select the correct one. It's kind of a weird naming for it. Okay. Hey. Hello world over and over again. All right, so it's alive. That's good. I keep getting notifications that this thing is ready. It makes me think something's wrong. Yep, there it goes. It resolved that port. It was named something weird earlier, but it looks like everything now has installed. The driver for Windows is on the chip here, so when you plug it in, it installs the driver. And all those notifications have to come in. Okay. So what's next? So controller. Communication. Sorry. And then we got to set up our ports and things. And then I'm not even sure when this is all said and done. I'm not even sure that I'm not sure this is gonna be that complicated. And if everything's being done by interrupts and callbacks, we may not even have anything in the main loop. It may just be an empty loop. Can somebody tell me how the music volume is? Just curious if it's loud enough or what. or too loud. I was messing with some settings, and I don't really have the output here for me to hear, so I can't tell. All right. Set up buttons. You know what? I don't actually remember how to do this. I almost never do like generic stuff. It's okay. You can hear. Okay, cool. Glad to hear. Glad to hear it. Set pin. Okay, here we go. Okay, so we got to go through. So it's pin mode, and actually let's go up here and define this stuff. So, oops, switch 1 is 4, and actually I need to pull up our schematic here, and I'm going to pull this over the side. Switch 1 is pin 4. No, 2. It's actually 2. It's labeled 2. Okay. I know we don't have the other buttons on here, but I don't see any reason why we can't just go ahead and define it and start getting all the software in place. Okay, and then we need to define the analog pins. So this one, CC19, is 14. Is that 15? Yeah, and then 16, okay. Okay, and then, man, it's been so long. I know it wasn't that long ago we did the Falcon project, but even then we weren't doing anything directly with just basic GPIO. So I don't actually remember how to do any of that. Luckily, Google helps. All right. Pin mode. One. Actually, you know what? These need to be redefined. I don't have... Okay. Hang on. I need the block diagram. I need to know which of these switches are play, pause, stop. Of course it wants to update right now. Okay, the schematic, the block diagram doesn't have it, but the, here we go. Play, stop, record, function. All right. Play, stop, record, function. Switch 1, 2, 3, 4. Okay. And then these ones are already defined as appropriate. So, all right, that'll be a little better. And then down here, play, And then we want this to be input. And then I think we can also define a pull up here. Let's see. I'm looking through the documentation here. Input pull up. I think that's an option. All right, hold on. Button mode. Input pull up. Yep. Okay. That's what we want. And then I don't know if this will have a mode yet, but we'll go ahead and define it anyway. Okay. All right, and then we actually need to do this for all of the buttons. Oops. Okay, and so play, stop, record, and function. All right. Set up sliders. And then I got to figure out how to do an analog read. I'm sure there's examples for all this stuff, and I'm just neglecting to do that. Okay, let's see. I can probably move this over some too, since I'm working on the computer more. I really need to get another camera so that I can have one focused on the stuff right here, and then get another one. Let's see. Need a code example. Here we go. Looks like you don't even have to set the pin mode. You can just call analog read on a specific pin, and then it gives you the value. There's just so much noise coming from upstairs. Yep. Interesting. Okay. Well, I guess we don't actually have to set anything up then. We just got to read. All right. And then finally, let's see. Trying to think of the best way to do this just to test everything. I guess with some globals. I don't actually know what values that function will return, that analog read. So let's find out. All right, let's see. Value equals 0. and then bool play pushed equals false. 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 There it is. Always takes me a minute to figure that one out. All right. Okay, so first things first, I guess we check the button. Basically, I wanted to print something to the serial port every time I push the button. So if read okay, so if digital read, now see what this would do right here is if it's high, it would return true. We want it to be if it's low. So if digital read and play pushed is false, then play pushed equals true. Dot print play pushed. All right. Oh. Okay. So that looks good. And then we need, oh, I probably should label this. So button. We need to basically check out all the states, right? Else if I can just copy this. All right, so else if digital read play, so if it's high, that means it's not pushed. And if it references as pushed, then we need to update that state. This is probably a roundabout way of doing it, but it should work. Let's just go ahead and say something here. So print, and we'll just say play released. All right, there we go. Okay, so now the other states. It's false. I don't know if there's any other states. What would the other states be if play was not pushed and it was high, then it just stays the same. It stays false. Yeah, I think we can leave this as is. Later on, we may want to put like timing checks in here, and that'll physically put like a software debounce in. All right. Slider. All right. We're probably gonna need two values here. Last value. Okay. Equals analog read. And this is the CC19 channel. If C19, yeah, value Does not equal CC19 last value. All right, then we want to update it. Slider is and then we want to do CC19 value. I'm all over the place tonight. And then we would just need a new line. And then we have to update our value. Or, yeah. Okay. I think this does everything we would need it to. Let's see if it compiles. Make sure I didn't forget any semicolons. What do you know? Okay. There we go. And then upload this. I think that worked. Oh, it did. So, okay. So this is common with sliders, right? Like the value can change ever so slightly if it's like stuck between two, and you can see that's what's happening here. If I move it down, we can see how nothing happens. And that's because something is screwed up here. Dang it. All right, well, what happens if I push the button? I guess we wouldn't see anything because it's probably going so fast. Thanks, Hide White. Yeah, it's perfect. Everything has gone wrong. All right. Here, I need to move something. I got my phone on this little stand here so I can see the chat, and it's just like way in the way. All right. So this means we have a lot of debugging to do, but that's okay. Let's start with something easy. Delay, say 100. Slow it down some so we can at least see what's happening. And then I'm going to have to go figure out what I did wrong. Oh, I know what I did wrong. I plugged the ground of the potentiometer into the power. So it was just literally an even voltage all the way across. All right, cool. Let's upload this. And I'm going to stop making dumb mistakes, I promise. And let's try this again. Okay. So it's a little slower now because I put that delay in. And then if I move this down, hey, there we go. As I move the slider down, it goes to 0. And then move it back up. And it goes all the way back up to the 1024. So anyone that's curious, what that means is that this is a 10-bit measurement. Because the max value you can have in 10 bits is 1024. It also means that this is an unsigned value, which is good to know. All right, cool. So that part works. Now does the button work? No. Why doesn't the button work? Probably because I have it plugged into the wrong pin. There it is. And released. Okay. So if I real quick comment out this. It's always good to double check your circuits. Okay, there we go. Fire this up. All right, so now this should just be the... So if I push the button, play pushed. If I let go, play released. And you can see the debounce there. Apparently that delay function does its own little debounce. Yep. All right, cool. So we've proven that part works. So now what? Eventually I'm going to have to move things into different files, but I think right now they can stay where everything can stay in the main because it's not too big. I need to figure out how to do interrupts. Let's see, what would be the best way to do this? This matters too because depending on the platform, certain pins can be used for interrupts. Let's see here. What are the different vectors? All right. Maybe I can find it. Actually, there's probably even an example sketch here. Let's see. Examples. Whoops. TC4. All right. Oh, it doesn't look like it. They have everything super complicated, just not any of the simple stuff. Any like button. All right, that's all right. I can still Google stuff and figure it out, but okay. I'll pull this page up. This is what I'm looking at right off the PGRC website, which is the company that makes and sells this device. The peripheral, reset the interrupt flag, set the interrupt mask, enable global peripheral. You must include the AVR interrupt header. Interesting, okay. Clear interrupts, set interrupts. Mask, flag, okay. If anybody has any advice on this, let me know. We need to obviously use an external interrupt of some sort. They only give timer values here, though. But I'm just trying to remember how this is done on. Let's see. Maybe I'm just teensy interrupt. First input is the pin number. Interrupt 0 means to use pin 2. I'm just reading through the forum here. change. Okay. All right, so it looks like the function is just, there's a function called attach interrupt, which essentially is doing the right thing here. Yep, that is a function. We need it to be play is the button. Then we'll put the name of our function here, and then what the appropriate thing here is. Let's see. Falling maybe? Yeah. Let's see. I gotta look up the Arduino reference for this function. Yep, okay, so you can trigger when the pin is low, you can trigger on a change, you can trigger on a rising edge, falling edge, or when it's high. It depends on the specific board which of those are enabled, but on this particular one I imagine all of them are, because it's a pretty complex micro. So we just really need to come up with a name for our service routine. Void button ISR. Okay, so this will be oops, I don't even know what I'm doing. That'll be our service routine, and we just need to print off this thing. So we can put this in here, and that should be fine. Okay, and then we need to attach this. So use button ISR, and then I want this to be change. I think that's acceptable. I think we probably need to change. Eventually, we'll need to put a delay in this, and so we can have our own effective debounce. But that should work. All right, let's try this. All right, well compiled, so chances are good. All right, please work. Hey, yep, you can see that debounce really messing with you there. It does do better though. Okay. So that's being done by an interrupt now. It's not even checking. The program is not looping and checking if the button is pushed. It's just every time the button's pushed, it's causing the processor, it's throwing up a flag that tells the processor to stop what it's doing and then address this issue over here. Excellent. Okay, and I probably need to look back at this and see if there's anything. I'll look in a sec, but I need to figure out if there's an interrupt for the slide switch as well. All right. So what we want to do here, We need to define a debounce. Debounce. Debounce milliseconds. Okay. And we want to delay that. And then check the value again. And if it's different, well, actually, we want it to be almost continuous. Is it when it's when it changes state, but I can actually do either. I could do any of those. I can do when it's low, when it's high, when it's falling, when it's rising, or when it changes. Those are my 5 options. So any scenario. Ah, shoot. What is the elapsed millis or whatever it is? Is it elapsed milliseconds? There it is. All right, we'll say debounce timer equals 0. Okay, this is how we're going to do this. While debounce timer, I'm doing Python again. While debounce timer is less than our debounce, and then I guess we got to define this. I don't know, 100? That's probably good. That's a pretty big debounce. It's millis. Basically, if we read the pin and it's different than whatever the value was when we started up here, then we want to return. So if we can just actually copy this. Play. Then return. Just return. Okay. And then we want to do the opposite of that down here. So basically, if during this timer it changes state, then we know that it's bouncing and we leave. And then we'll come back in here if it goes back down again. Is the theory. I feel like there's better ways to do this, though. I should probably look at like an example of a software debounce. I'm sure somebody has come up with a ingenious little solution that makes way more sense than mine. Turns out you need your semicolons. All right, excellent. Okay, that looks good. Let's upload it. Look at that. Push, release, push, release, push, release. There's not a bunch of them pumping. It's not bouncing anymore. It's still pretty fast, so I can push the button really fast. Okay, that's cool. Awesome, that worked great, actually. Ha! And no resistors or capacitors required. Just a few lines of code. And I saved myself 25 cents in parts. Well, $1 if you count all of them. I'm just trying to see if I can mess it up. But it just seems to be super reliable. I might need to disable interrupts and then re-enable them when I'm in the middle of that thing. Just in case, like, if somebody were to push down multiple buttons at once, I wouldn't want them, like, the interrupts to interfere with each other. Although I don't know how big of a deal that would be. Okay, so that looks good. Let's change the name on this. Play button, ISR. And then I probably need to do that for all of the buttons, which means I'm going to need variables for all the buttons. All these global variables are making my head hurt. It's not great programming practice, but it's also a very simple program, so it's probably not the end of the world. All right. Looking good. And then we'll have to go through and set up our ISRs real quick. Definitely when I'm all done with this, I'm going to move all this button stuff to one file, all the slider stuff to another file. All right. So play, stop, record, and one more for function. All right, and then let's go up here and fix all the little things. Stop, stop pushed. And stop released. If anybody has any questions or anything they want to talk about, now's a good time because this is going to take me a minute. It's looking like the SpaceX's Starship SN11 is going to fly next week. I'm really excited for that. Hoping this one sticks the landing and stays there. Doesn't unintentionally launch again. But I'm looking forward to that. Should be good. Let's see. Record pushed, stop pushed, stop released. I think that was good. Yeah. I think a lot of people are looking forward to it. Also, I don't know if we talked about this on stream yet, but Rocket Lab said they were going to build a Falcon 9 sized rocket, so that was kind of cool as well. I cannot wait to see that go. Okay, I think that's all good. Oh, I gotta attach all the interrupts. And then I guess figure out a way to check them real quick. Okay, let's just see if this compiles. Yeah, it did. Interesting. Yeah, I know. I'm not excited about those relight issues. The way they're solving them now is just relight more at the same time so that we're less likely to be in a situation where we don't have enough engines. But I would like to see like really good reliability on that so that that's not the case. I mean, it's obviously a great solution and probably should be done anyway as a safety feature. but I would like to see like close to, 100% reliability on the relight. Also, it seems like every static fire they've had to replace 1 or 2 engines. And I wish they could get that down to where it's just like slap the engines on, do a static fire, okay, it's good. Like almost 100% of the time it's good to go. All right. So play works, and then I'm actually going to move this wire. And we'll see if we can get another one of these to work. Oh, the stop release doesn't work. Why? All right, you're gonna have to fix that. Is that the same for all of them? How about record? Yep, something I've done has messed them all up. And then finally function. Yep, where it only pushes but doesn't release. Okay. Is it 3 or 2? I think it was 2. They light 3, drop down to 2, ride that down, and then go to 1 right before touchdown. But I don't know for sure. I'll have to look into that again, see what he said. All right, so why did this not work? Probably because I missed this variable. All right, same for this one. There we go. All right, let's try that. So now the function button should work. I don't think I uploaded it. I pray that was the problem. Yep, there it goes. Okay. Function looks good. Let's try record. Yep. Let's play. Did I miss stop? I think I did. Let's try stop. There it goes. If I push it really fast, it like stops working, but then it does as soon as I release, like whatever state I end up in. Yeah, it's the one. Okay, so that works out well. All right, so now I think okay, so next thing I need to figure out if there's an analog. And I don't know if it's gonna have it. So somebody has done it. I'm looking at an example here. Attach, interrupt, start receiving, rising, falling. No. That's not it. Okay, so it looks like the places where people have done it has been done kind of manually. So there's not like an Arduino. I thought they were going to throttle 3 all the way down. Interesting. I mean, maybe so. I don't totally remember what it was, what the plan was. Let's see. I might have to pull it. Yeah. Might have to start with that and see. Okay. Let's go off that then. So what would be the best way to do this? Obviously, we had a problem earlier where it was like, jumping all over the place. And we saw that it was really within 1. I think if it's within 1 or 2, we can probably safely assume that it's not like really changed per se. But if it changes more than like 2, it's probably way off. Okay. So I got to think of the best way to do this. I think they have to be float values anyway when we send them back, so maybe we should just go ahead and convert them. Yeah, that's a big problem. They're still consuming engine internals. It's kind of annoying when your engines eat themselves alive as they're coming down. I wonder why that is though, because it never looks weird going up. So like when it's going up, it seems to be running fine, but it's just after relight when coming down. I wonder if there's just something about that scenario or something that's just weird, or just like the movement of the vehicle during the relight is causing, like, I don't know, something to slosh around or something, and a bad reaction to happen. I don't know. All right. Let's change these to float values. And then I feel like 8-bit float values would make sense. Yeah, pressure really. I think that actually makes the most sense because they're using different tanks. They have to switch over, so there is something going on there. It'll be interesting to see how they go, though. And honestly, the most interesting thing is going to be what the final solution is. Once they try everything and land on the item that works, what does that look like? I'm curious. Yeah, I remember reading about that because of the bubbles and everything, which originally they weren't using helium, so that fix of using helium caused that issue, actually. So I don't think they plan to use that indefinitely, but I don't know what their plan is in the meantime. All right, so these are float values now. And then for our, let's see, what's our increment going to be here? I don't know. If you have a 10-bit value, I don't think we need equals there. Yep, 0.25. So you can take, I wanted to make it like a max of an 8-bit value, so 256 is the max. In order to do that, you need an increment of, multiply it by an increment of 0.25. Okay. So it should give you that value. So let's run this and see what results we get. Okay, so that worked. We're getting our 0 to 256. Or how accurate it is, or if it is logarithmic. So that's about in the middle. I guess it is pretty logarithmic. Oh yeah, it must be. Because it changes a lot on the low end here. If I move it a little bit on the low end, it changes dramatically. But on the high end, it barely changes at all. And if I put it, like, eyeball it to the middle, you can see it's still above 200. It should be at 128. Where is 128? It's hard to hit, but it's about right there. And honestly, I think they're supposed to be logarithmic the other way. I think the higher value is supposed to be a big change. So I might have to flip this around, at least in this circuit. Interesting. Okay. So that part's working. So now we got to figure out how to resolve this. It seems to be jumping between two values. I think I know how we can do this. Does it ever jump between 3? Yeah, you can kind of get it too. You would expect them to scale that way. So big change on the low end and small change on the high end? Or is it the other way around? Small change on the low end and big change on the high end? Okay. So this is a way of doing kind of a... Yeah, I mean, that makes sense, because these are audio controllers, and 99% of the ones you buy are logarithmic. So we'll see. I'll ask the customer and see what he says. And if he doesn't know, I'll Google it. All right, so let's do this. Let's see. Temp. Slide. Value. All right, and then what we're going to do is do like a moving average kind of function. And so how that's accomplished is you take the new value, multiply by the new weight, and add the old value, multiplied by the old weight, and the weights together must add up to be 1. Okay, and so what this does is create a new value that's should be equal to the pretty close to the actual, but it moves, the speed of the movement depends on the weights. So the higher the value of the new weight, the faster it moves. The higher the value of the old weight, the slower it moves. I remember these will always, adding new weight plus old weight always equals 1. So when you raise new weight, old weight goes down. So it's a way of adjusting the rate of the average. So I think that works. Let's make sure it compiles. Semicolons are important. Okay, and we'll upload this and see what we get here. Okay, interesting position. I think I've messed up my, but you can see that there's a little bit of movement, but less. It seems to be sticking better with wherever it's at, and we actually have a pretty in-depth thing. I gotta figure out what I did here because my values are not coming out correct. The max is like 51. What did I do wrong? Oh, the old weight is equal to 0. It seems to be what is happening here. Because this defined, for whatever reason, 1 minus new weight is returning 0 instead of... That must be what's happening. Weird. Let's test that theory. Change this to 0.75. Okay. Try again. Yep, there we go. So you can see in the start here, I don't know if I can hold it there. Yeah, I can't. But it started off low and then climbed up because the switch was already high. All right, so now if I move this, it's still moving around a lot, which is concerning. But it is weighted towards the well, actually, I don't know that it's weighted towards the new end. It's Okay, well, this moving average smooths it out some, although it doesn't look like it much. All right, so we need to come up with a solution for that. I think what we should put in is some sort of variance that calculates if the change is less than this, then don't change. We can also change this a lot to make it really slow. 0.01 and 0.99. Upload that, and we'll see it trickle up really slowly to the 255. There it goes. Hang on, we're almost there. I'm curious to see if it actually, how close it stays then with that weight. And as it gets closer, it's going to taper off, so interesting. Almost there. This is exciting. Oh man, it's taking forever. Because it gets slower and slower. This would be a really annoying value to actually use. Because as soon as you change it, it's going to take forever for your workstation to realize that. All right, I'm just going to move it down. I'm tired of waiting for it to go up. So then if I move it down some, it starts dropping. If I change it a lot, it changes. It takes forever, though, to get to a position. Here, I dropped it all the way down. You can see it. There, I put it right at about where it's already at. That's really annoying. I think our 25-75 method worked a lot better. But also this old weight doesn't seem to... I can't make it depend on the new weight very easily, so I'm going to drop it down here. I'm just going to create a variable in the function for it. There we go. All right, so that should do what we want it to. Let's go ahead and upload it. Interesting, that's right about where it's supposed to be. Still moving around quite a lot. Also, did I forget to change this up here? No, I changed the new weight to 0.25. Okay, so if I move it, it should move pretty fast. It still is a little slow. Honestly, somebody using this would probably want it faster than that. Let's try 0.5. Whoops, didn't mean to do that. It's a little better. The key is to see when I stop moving how long it takes it to catch up. We'll have to play with that. Okay. So now we need to introduce some sort of variance value. What is our variance? Yeah, that's what I'm working on now. It's noisy, but it's better. Like, if you look at the values of the noise here, let's look at this real quick. You can see that the change is relatively minor, like within an actual increment of the analog. So 0.2 is probably a good variance then, because if it switches to, if the analog reads a different value consistently, it will fall outside of that because it's a 0.25 difference. Okay. So if this value minus this value It's greater. We need to do an absolute value. Greater than the variance. And then how do we do... So do we not have math functions? ABS is the function. Okay, so if the absolute value difference is greater than the minimum variance, then we go to the new value. Maybe this will work. Maybe not. So minus last value. Why is that? Oh, I still have a delay in here. That's why that's running so slow sometimes. It would be way faster if I didn't have that. All right, I'm going to take that delay out eventually once we get this working reasonably well. But first we need to do that. So I guess, here, let me just do this. I'm just going to print all these values. Okay. Oops. Don't forget a semicolon there. All right. Can you display the binary value next to the decimal? I can, but what I'm doing here will effectively do that same thing. And then I want this value too in case this calculation is weird. All right, let me upload it. Let's see what we get. I didn't think this through very well. Okay, oops. I just wanted new lines between each one. That one stays the same. All right. Try that again. Okay. Okay, so our variance is being calculated correctly, it looks like, but it's always just outside of what we decided our max could be. So despite that one attempt, it's actually a lot bigger than expected. Odd. I wonder if that has to do with our weights. Like if we weight it to the old value more, that would actually lower that variance. Let me try that. Let's make it 0.25. Okay, we're not getting huge numbers this time. Better. Let me lower it a little more. 0.1. ends up in mostly the right spot. See if I move it all the way to the top. It takes a little while to get there. Okay, it froze, meaning the variance was underneath what the max was. So we've cleaned it up a little better, but moving it around still has an issue, kind of. All right, since this is getting better, I'm gonna change this to 0.05, and then I'm gonna drop this delay down to like 1 millisecond. That'll let it go run really fast anyway. There we go. Okay, it's still moving some. That's disappointing. It's better though. If I move it, you can see it change. It stays pretty small if I don't touch it. I wonder if I change that variance a little more, or up that max a little more. So if I take where's the max? Here. 0.24. All right, not touching it. The capacitance for my fingers is what changing it is what is changing it now. But if I let go and just stop touching it, okay. Well, even when I get close to it. Is that really a thing? No, okay. I was like, is my ring doing that? All right, so it's better. So now I think I can take out this stuff since I know this is all working. Verify this. Upload it. All right. So now our slider. Oh, that's way better. So stop. All right, move it again. Move it down. Move it up all the way. And then all the way to the bottom. Hey, it was responsive and almost like no noise whatsoever. Excellent. If I touch it, the capacitance changes the value. But yeah, we got there. Okay. Interesting. I wonder if it'd be worth putting a capacitor on that line anyway. Just to help a little bit. It's still moving around slightly. And like, I get the feeling that the way this works with it having to be outside the variance to change, shoot, what was I going to say? I'm worried that it's going to, like, you're still going to be at a point to where, like, the two values it's measuring are just outside the variance from each other. So it's still, it's hard to describe, but it's still going to flip occasionally because it can only ever change by a big amount. So if it does change by a big amount, then it's got to change back and so on and so forth. When the true average is really right in the middle. So how to fix that? What if here, we still did this part anyway. Last value, or new value equals last value. But we only sent it whenever there was a big change. I feel like this is like, this has the obvious case. Oh no, I think I have to do this afterwards. Where if you move the slider super slowly, then no change is detected. But I don't know if that's really possible with how tiny of an increment it measures. Like even just touching it causes it to change a lot. All right, let's see what we got here. Oh, but it measures so fast that it does break it anyway. There you go. If I move it really fast, then you see a change. But I have to move it really fast. Okay, so that's not an acceptable solution. Although it does show that my theory is correct, that because now it's not changing at all. Okay. Oh, because the delay only happens on a big... What if we take this out and put it outside? That at least adds some delay. I still don't think it'd be perfect, but it should do better. Okay. Yeah, you don't have to move it as fast. I could put a bigger delay on it, but I really don't want to do that. But I'm going to. Bigger delay lowers the performance, so I don't think this is a permanent solution. Yeah, that did help a lot. Man. It's like when I stop moving it now, it just stops. I still don't like this solution though, because I feel like if I move it really slow, yeah, I can get it to not work. And that's not going to be acceptable. All right, so what would be the best way to do this? Stay at a moving average and constantly update the moving average, but don't change unless there is a big change. Maybe it's more acceptable to lower the variance now? Because that's effectively what that would do. But I feel like this is still... All right, does this work? Yeah, it does kind of. But I can still move it really slowly and have a delay. Yeah. Yeah, I just don't like that. That's not a good solution. All right, delay's taken out. This goes back here. You know, they make these things called rotary encoders. I wonder if you can get linear encoders, which are basically like the rotary encoders. It probably isn't the right thing for this application, but they're like rotational potentiometers. And as you rotate them, you can feel a clicking. And every click, they send out a signal, a high-low transition. And you just count that with the micro. And you can actually get a very accurate, without any noise representation. In this case, though, I think it would lead to some weird behavior if you had something. Well, it just wouldn't feel right? Because the sliders don't ever feel like that. All right, let's see. I know I can come up with a solution here. We always update the value anyway, but we only print it if it's vastly different. But that doesn't work. Maybe we have a variable for last printed value? That might work. Float cc19 last sent value. The sheer number of variables is going to get ridiculous. I'll eventually move this all into its own thing, create classes for all the different sliders, and we'll create objects, or create a class and then objects for each of the sliders and whatnot. All right, so if this does not equal the, or hold on, let's not get ahead of ourselves here. If this, wait, no. No, yeah, we actually do want that there. Okay, and if all right, just trying to think through this. By now I should have just Googled an algorithm for this. That probably would have made more sense. No, wait, hold on. I think this is right. Hold on. It's not equal that. Okay. And this should be last value sent. Okay, so we check if the value equals the last value. If it does not, then we update that last value. However, we don't send it unless the last value sent is greater than the variance, or if the variance, if this value is greater than the variance on this one. This feels just like a roundabout way of doing what we were doing before. I don't think this fixes anything, actually, now that I'm thinking through it. Okay. Yeah, it is. So what's the right way to do this then? I don't know why I thought this was a good idea. Like, now that I'm thinking through it, it's just the same thing that we were doing before, just with more variables. So, a worse solution. Unless we do 2 variances. Maybe that's the secret. Slider minimum variance, and then maybe like a cent minimum variance. This is the only way I can think of this being like correct, or a good, a different method. Okay, let's try that. Oh, and then I need to update it. Maybe this does something different. That was not declared in the scope. What was the value? Last cent value. Of course it was. All right, go. Oh, upstairs neighbors are moving furniture. Yeah, it's still really sensitive when I do that. Yeah, because you can definitely get stuck in the middle of things. I mean, it's still kind of working like it's supposed to. All right, there's got to be another. I'll have to do some research on this. We're getting at 2 hours anyway, so I probably need to be done here soon. I need to eat some dinner and everything. I'm getting tired. But we're getting there. We've got it kind of working. I can show that the push button works here. Interesting. All right. Well, I think I'm going to call it here for tonight and look into this. I'll do some research and see if there's a obvious like solution to this. I don't know that there is, but I'm sure there's a standardized algorithm or something for this specific scenario. And we'll see what happens. But yeah, so I will be back on Tuesday, back on the normal streaming schedule. And this has been good. We've gotten our circuit kind of proven that our circuit does work. We just need to make sure that we can do this well without there needing to be any changes. And then we can, so once I can show that I can move the potentiometer around without having any noise, then I think we'll be ready to, we'll be ready to start designing the circuit board and stuff. And I really, honestly would like to get a lot of the code in place too, just to learn how that works as well. So I'll do a little more research over the weekend and we'll see what happens. But thank you for joining me tonight. I had fun and it was nice to get back to this. So I will see you all later. Bye.